Hi, this is Mr. Marquitos. In this class video, we are going to review problems that are somewhat similar to the ones on the Unit 4 exam. So let's jump right into it. Consider the function f of x is 4 times e to the x minus 3. Part A, state the equation of the horizontal asymptote to the graph of f. We know that the value where the horizontal asymptote occurs in an exponential function's equation is that constant that is added or subtracted to the end of the equation. So therefore, the equation, and it's a horizontal line, so it's y equals is -3. Done. B, the range, remember the horizontal asymptote definitely plays a major role in the range of an exponential function. This exponential function would increase because the base, remember e is about 2.718, that's Euler's number. And so the whole graph should be above the horizontal asymptote. So the range would be that y needs to be greater than -3, or if you prefer interval notation, y belongs to the interval -3 to infinity. C, find the y-intercept algebraically, so we must plug in x is 0 and see what value comes out. So we have f of 0 is 4 e to the 0 minus 3. E to the 0, anything to the 0 is 1. So we have 4 minus 3, which would be 1. So my y-intercept is at the point 0, 1. That looks pretty crappy. We'll fix that. Okay, there we go. D, find the x-intercept algebraically in terms of ln, the natural log. So don't get a rounded numerical answer, but actually leave the final answer in terms of ln. So part D there, if we want to find an x-intercept, we must take our function f of x or y and set it equal to 0. So we have 4e to the x minus 3 equals 0. I would add 3 first. 4e to the x is 3. I would divide by 4. E to the x is 3/4. And right, if I want to isolate the x, which is stuck in the exponent, I would have to log both sides. So I'd have ln of e to the x equals ln of 3/4. And the inverse nature of e to the and natural log, which is base e, undo each other. And so we are left with that x is natural log of 3/4. And the last question or part of this question here is to draw your sketch. Now, again, I won't go through this too much in this video. Maybe we'll just do it for the first one. But I can absolutely use Desmos definitely here to help me come up with a good sketch, especially if I'm a little uncomfortable. So I'm going to go graph 4e to the x minus 3. So we have, what do we got? You can even do f of x equals. That's kind of nice. So it's 4, and I'm going to use the letter e for base e to the x, and then take away 3. So again, it shouldn't look much different than a lot of other exponential functions. By the way, that's that negative 0.287. That's ln of 3/4 there. So I just have to put that all together. And the key features I have already determined from doing some algebra or analyzing the function's equation. So I like to put my horizontal asymptote first. So drawing my dashed line here. And of course, you should label it. So it's y equals -3. Then the x-intercept here, that's the ln of 3/4. I'm going to mark that. And then the y-intercept is at 0, 1. So it's not enough just to put dots there. I need to say like, hey, this is at ln of 3/4. I have to tell somebody that, hey, this is at 1. Because without a grid, I really have no way of telling where those should be just by looking at your sketch. So the last thing, and so you notice how I put in all the key features first, and then I draw in the graph. So it's got the exponential function growth shape. It doesn't look super pretty, but that's good enough. Make sure you put some tails on the ends of those graphs, arrows. Cool beans? Not too bad. Number 2 is a very similar question to number 1, except of working with an exponential function. We're going to work with a logarithmic function, but also similar. So consider the function g of x is 2 log base 2 of x plus 2 minus 4. State the domain. The domain, right? We need to make sure that the argument of our logarithmic function is always positive. So I need the argument, which is x plus 2, to be greater than 0. And if I subtract 2 from both sides, I get this statement, which is x is greater than negative 2. That is a fine way to leave your domain. You're stating the domain as an inequality statement. That is fine. I see some people kind of come down and they're like, oh, so it's this. You could put that here if you want. It just says state the domain. So either of those is totally acceptable. Okay, state the equation of the vertical asymptote. We know that's going to happen when the argument, that x plus 2, is equal to 0. So if I subtract 2, my vertical asymptote is at x equals negative 2. C, y-intercept, not different from before. It's a different function, but to find any y-intercept, I substitute x is 0 and see what I get. So 2 log base 2 of 0 plus 2 minus 4. 0 plus 2 is 2, right? So I have 2 times log base 2 of 2 minus 4. A lot of 2's going around. Log base 2 of 2 is 1 because 2 to the first is 1. So I get 2 times 1 minus 4. That's negative 2. So my y-intercept is at 0, negative 2. Okay. X-intercept, right? So it's a lot of the same questions. Obviously, like logs have vertical asymptotes where exponentials have horizontal, but really like I'm doing the same kind of analysis on the function to obtain all of its key features. So D now, if I want the x-intercept, I have to set g of x or y equal to 0. So I'm going to have to solve this equation. 2 log base 2 of x plus 2 minus 4 is coming out to 0. So we're going to add the 4 over. I almost lost my 2 in the front. So that equals 4. I'm going to divide by this 2. So now I have log base 2 of x plus 2 equals, 2? And then, now this is the thing that mystifies people. There's this switch that happens, but one way I kind of tell students to do this is that you're really doing this the same way you do any other equation. How are you getting rid of log base 2 on the left-hand side? You're using the inverse, right? So you're undoing log base 2. How do you undo log base 2? You're like exponentiating both sides with a base of 2. That's how that sort of happens. It's not magic. On the right, you have 2 squared, which is 4. So I get x plus 2 is 4, so x is 2. Therefore, my x-intercept would be at 2, 0. So now, right, just sketching it, and again, when I'm sketching, I've really done all the work. I know where all my key features are. It's just really a matter of putting it together in a nice, concise way. So I like to, like I said, I like putting in my asymptotes first. So I have a vertical asymptote here as a dashed line. This is at x equals negative 2. I have a y-intercept at 0, negative 2. So I'm going to do that, and I'm going to put a little value there. Negative 2. Over here, you have an x-intercept at 2. Again, I'm going to mark it, and everything's there pretty much. The only thing left to do now is to actually draw the graph, which is kind of like filling in the blanks in a way because everything is already there, ready to go. And I make sure I put my tails. It would be nice if I put like y-axis, x-axis, but hey, right? That is a good sketch of this function. Cool beans, right? Key features of an exponential and a logarithmic function, finding them and graphing them, very important. Number 3 here, consider the logarithmic function L of x is 2 times ln of x minus 3 plus 4. Find L inverse of x, so that's the inverse function algebraically. when we have that function notation here, L of x, I do tend to tell students, hey, it might not be a bad idea to change that to y. That is what it is, but it feels better when you do the next step down here, because my next step is to swap the places of x and y, interchange those inputs and outputs. Okay, plus 4. Now my job is to solve for y. So I have to subtract 4. So I have x minus 4 equals 2 ln y minus 3. I would divide both sides by 2. And I would just leave that like x minus 4 over 2. That's perfectly fine. Equals ln of y minus 3. Much like before here where I wanted to undo the log base 2 up here in number 2. A lot of 2's. Here I want to undo the natural log base e. So I undo it by exponentiating both sides with a base of e. It's still doing the inverse to both sides. That is the only way you ever isolate a variable in solving an equation. I just think here it doesn't feel as simple as like, oh, you have x squared, square root. It's the same concept, it's the same process, it's just different functions with notation that you're not particularly thrilled about. So what are you left with? You have e to the x minus 4 over 2. All of that is up in the exponent, and that's equal to y minus 3. So if I add the 3 over, I will have isolated y, and therefore I could say that the inverse of L inverse of x, is e to the x minus 4 over 2, take away 3. Cool beans. Now, B is a very general and important fact about inverses, their functions, and composition of functions. And although we know what the answer is going to be to this, what happens when you compose a function and its inverse, what I would say is you're not just saying what the answer is here. The request is what is called a show that, which is basically almost like a baby proof. So this is tedious, and I don't think we like it a lot, but it's something to be good at here. So you're asking me to find L composed with L inverse, looks like law of x, LOLs, which really means, right, you're looking for L of L inverse of x. In other words, you are putting L inverse, you are putting that in for x in L of x. You're just substituting another function. So you can even go a step further here and say, well, that would be L of e to the x minus 4 over 2 minus 3. This is not the most enjoyable thing to do. It's a little tedious. But what you want to show happen in each step now, working downward, is that you should see each piece of that function's equation start to get canceled out with things here until it boils down to just plain old x. They should perfectly undo each other. So L of that lovely thing would be 2 ln. Okay, in place of this x goes this entire expression. E to the x minus 4 over 2. I messed up. I'm glad I caught myself. It's interesting, by checking this, I caught my mistake, which is good. Somebody's commenting on the video. He made a mistake and he didn't see it. I would have had to add this 3 over, right? It should be plus 3. So this should be plus 3. So it's plus 3, but right then built in is minus 3. So I have that here, and then outside you got a plus 4. Now step by step, things should go bye-bye. So first the 3's go. So I'm down to 2 ln of e to the x minus 4 over 2 plus 4. Now, this is, and again, somebody who will ever watch this video says, he's talking nonsense here, but essentially ln and e are opposites of each other. So when you get them quote-unquote next to each other, they undo each other. So the ln and e go bye-bye. Now you have 2 times x minus 4 over 2 plus 4. Oh, the 2's go bye-bye. And then you have x minus 4 plus 4, and the 4's go bye-bye. And you're left with just x. So it's a bit of a proof, right? It's not like, hey, just tell me what the answer is. We know what the answer should be. It should just come out to x. Cool beans. We'll move on to the next one. And I think 4 is everybody's least favorite question. We'll see. So this is that percent manipulation stuff. Nobody really likes that. Leona is putting together a puzzle such that every 5 days she places 25% of the remaining pieces into the puzzle. That first sentence hurts my brain a little bit. If she started with an 800-piece puzzle, how many pieces are left to be placed after 23 days? Show the work that leads to your answer. Yikes. So, right, every 5 days she uses up 25% of the remaining pieces left every day. So I kind of like writing this stuff, right? So like, the thing they actually told me is what we call the multiplier for 5 days, which would, well, they indirectly told me it would be 1 minus 0.25, which is 0.75. That's for every 5 days, right? So the problem is that, like, I don't like that particularly because, wouldn't you like to know what percent of things she does every single day, especially if you're going to ask me like a random amount of time, like 23 days? So the multiplier for 5 days is 0.75. So I would like the multiplier for 1 day. That would be that rate, and right, so you're kind of going from big to smaller. So it would be, because there's 1 day out of the every five, right? It's 5 days for 5 days. There's 1 day, right? So it's 1/5. Now that is the multiplier for 1 day. If I know, and you might say, like, should I stick that in my calculator? I would not. I would actually leave it this way, because now, so like after 23 days. I can tell you what the multiplier is. It's 0.75 to the 1/5 power, so that's for 1 day. If I raise it to the 23rd power, that would be for 23 days now. So that would be 0.75 to the 23 over 5, and that, I have to put that in my calculator. So 0.75 to the 23 divided by 5 is this percent, which, I'm going to cut it. Yeah, we'll put maybe one more decimal place. This is the what remains, or let's put percent that remains after 23 days. So how many pieces are left, right? How many pieces are left? That's what they're asking. So it would be the 800 she started with times that decimal. And since we're talking about puzzle pieces, and you really shouldn't have half of a puzzle piece unless your dog ate some of it or something like that. Haha, I made a funny. We should have a whole number answer. This comes out to about 213 pieces. I think people don't like that question. And I think it's because, especially here, you have to manipulate the rate to be effective for a different time period twice, right? Because first you start out with the 5-day multiplier. Then you figure out what the 1-day multiplier is, and then I get the 23-day multiplier. Lovely. Anywho, okay, moving on, so we don't sit here and listen to all this forever. Number 5 here, little laws of logarithm action here. So if big Y, capital Y, is log base y of c, determine the value of each of the following expressions in terms of y. Okay, this is just my laws of logarithms, but I don't know, sometimes this really beats people up. So you have log base 6 of c to the 7th. I'm going to use that power law with the exponent of 7, bring it out in front as a coefficient 7 times log base 6 of c. Log base 6 of c, they are calling y, so I would say that's the same thing as 7 times y. And, right, my final answer is an expression in terms of y. I am done. I mean, there's no way to simplify that either, right, but I am done. Okay, B. Now you got log base 6 of 36 times c to the 4th. Given that I see that product inside the argument, I'm going to use the product property. So it's log base 6, 36 plus log base 6 c to the fourth. So log base 6 of 36, 6 squared is 36. So log base 6 of 36 is 2. Crazy, right? It's fun to say that stuff fast. And this 4, like before, can come out in front as a coefficient. So that's 4 times log base 6c. And once again, log base 6c is y. So it's 2 plus 4 times y. I know this doesn't have a y in it, but overall, this is an expression in terms of y. So that is, again, an acceptable final answer. One more here. They're not terrible, and if you're comfortable with these can be done very quickly, but we can understand how this might not be the most comfortable thing in the world. That's okay, though. You can get comfortable with it. Log base 6 of c to the fifth over the square root of 6 cubed. Yuck. Now I'm seeing a quotient, so I'm going to use that quotient property for logarithm. So I have log base 6 of c to the fifth. If you want those parentheses there, by all means. Minus log base 6 of the square root of 6 cubed. Lovely. That 5 here, let's pull that out in front as a coefficient. So that's 5 times log base 6c. We could change that to y in a minute. And then I'm going to start working on, this root business here. So that's 6 cubed to the 1/2. Okay. Remember, log base 6 of c, they told me that's y. So that would be 5y. So that first expression is donezo. Here, I have log base 6 of 6 cubed to the half is 6 to the 3/2. And that there is this undoing here. You have log base 6 of 6 to the, they kill each other off. And so my final answer here, I think, is 5y minus 3/2. Hopefully I didn't mess that up. No, I'm good, I think. Anywho. Okay, 2 more. They're doozies. Sorry. 6. One thing, of course, which we didn't have initially when we learned about growth and decay models was the logarithm. And now I can use the logarithm to really help me solve exponential equations. And maybe I even create those exponential equations using growth modeling. So a population of a specific bird on a tropical island is growing continuously at a rate of 4%. I could have given you any rate, but I picked growing continuously for a reason. If somebody tells you that something is growing continuously, that tells you that the base of this exponential function is e, okay, per year. Anywho, when researchers began analyzing the bird population, there were 400 birds present, right? So this is exponential growth with a base of e. A, write an equation B of t, the population of birds at time t. So without just straight up coming up with the equation immediately, it's going to look like this. It's B of t is equal to B sub 0. The difference is instead of having 1 plus r to the t, that would be if it's just some normal growth percentage. But this is continuous growth, so it's not 1 plus r, it's just e to the rt. And then I just plug in the stuff they told me, and I should be good, right? So what's B sub 0? 400 birds present initially. E to the, what's R? It's this percentage as a decimal, so that's 0.04t. That's it for part A. That is the model. I just came up with it. I'm done. B, to the nearest whole number, determine the number of birds present on the island after 5 years. Okay, I mean, that's kind of a natural question. So you're looking for B of 5 because T is 5 after 5 years. So that would be 400 e to the 0.04 times 5. Now, to be quite honest with you, even on any not even my test assessment, or any standardized thing, at this point, maybe you're like, oh, I could, multiply these and something like that. Yeah, great. But you know what? You're really not going to get a numerical answer out of this without a calculator. So at this point, once you've shown that 5 has been substituted in your function, I would just type this whole thing in my calculator and give an answer. So it comes out to I'm rounding a little bit, but it's 488.56. And since we're talking about birds, and they actually said it here to the nearest whole number, we're going to say our final answer is it's about 489 birds. That's how many would be on the island after 5 years. Cool. C, we'll need a little more room, is, and again, very natural question. If you're, some type of biologist studying population of bird in a particular environment, natural question to say, hey, to the nearest year, determine the number of years it would take for the bird population to double. Completely natural question. So what you're saying, or what they are in the question in C, is they're trying to figure out at what time t will b of t equal double. We started with 400, so double would be 800, which means I have to take my exponential function, my growth model here, and set it equal to 800. So I have 400e to the 0.04t is equal to 800. Okay, I would divide both sides by 400, so I have e to the 0.04t equals 2. And then sort of this magical thing happens, right, where I use the log that is the same base as e, which we call ln. I do it to both sides, because, right, anything I do to one side, I'm always doing to the other anyway. And this beautiful, cancellation happens. And so you have 0.04t equals the natural log of 2. And if I divide by 0.04, I get ln of 2 over 0.04. So that is the exact answer, but obviously, that doesn't really mean much. So you put that into a calculator. And by the way, right, if you needed to do that, maybe we'll do that here. I'll hit the divide key first to get a fraction. If you just type in ln, Desmos knows it's ln, so it's ln2, divided by 0.04, and you get about 17.32, roughly. So 17.32, la 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 la. To the nearest year would be about 17 years. Cool. So there's your modeling, exponential modeling, together with solving exponential equations using logarithms. Lovely. Okay, last one, which was the very last topic we encountered, which was compound interest, which is an application of exponential growth with a slightly modified formula. So maybe we'll just drop this over here. If you have an compound interest situation and the number of compoundings per year is n, the formula is a of t is p, the principal, times 1 plus r over n to the nt power. Okay, so looks like there's a couple of things going on here. A, for number 7, so you would like to invest $5,000 and have two investments to consider. Account A pays 4% interest compounded annually. So we'll have account A here. Okay, so lots of interesting things here. They told me what P is. It's $5,000. That's your principal. That's your initial investment. They told us R, which is the 4% as a decimal. And they told us one other thing. They said that you're going to compound annually. That means you will compound once per year. So N is 1. I pretty much have everything. So part A, write an equation for S sub A of t, the amount of money in the account A at time t. So it would be S sub A of t is 5,000 times 1 plus R, 0.04, over n, but n is 1. We'll put it there, to the 1 times t, n times t. So I would probably make that look a little bit cleaner, right? It would just be 5,000 times 1.04 to the t. Okay, B, find the amount of money in the account after 20 years. Okay, again, natural question. You invest some money, maybe you're planning for a long-term investment here. Maybe it's 20 years. So I want to find the value of S sub A of 20. Time is 20. That's 5,000 times 1.04 to the 20. And again, right after that, there's really nothing to show somebody. You're not getting any type of numerical answer out of this by doing it by hand. I'm just I'm like, 5,000 times 1.04 close parentheses to the 20, right? I'm not really like going, crazy and saying, oh, let's do all these crazy things. Just, right, put it in and that's it. Just write down the answer, round to the right place. It's $10,955.62. So we'll put that there. So S sub A of 20 is 10,000, so it's a little more than double, $955.62. Again, right, like you might be like, that's not great. It's not, but that's because you only invested $5,000. I mean, in 20 years, your money doubled. So if you invested $1 million, you would have over 2 million. So, I mean, it depends how much you start with. But yes, if you want money, you have to, or if you want to make money, you have to already have money to invest. Life. Anyway. Okay, part C now. Part C is algebraically, which you're going to hear me say that a lot on the test. Algebraically, find the amount of money in the, determine the amount of time it will take to double your money. Again, a natural question. I mean, I guess it's a little less than 20 years, but we can find a very exact time by using our logarithms here. So we're trying to figure out when is it that the account at time t, when will that come out to double my 5,000, which is 10,000? So, all right, I'm taking my function, which is 500 times 5,000, 1.04 to the t is 10,000. I'm going to divide both sides by 5,000, so you got 1.04 to the t is 2. And now, right, like, the base is not a great number, right? It's not e, and it's not like something like 2 or 5. 1.04 is not my favorite number. We learned that you can use any base logarithm you want. So in this circumstance, people heavily tend to choose base 10 log. So they're going to go they're going to take log of both sides. Okay. The t I'm going to bring out front as a coefficient. So that's t times log of 1.04 equals log of 2. And now I can divide both sides, right? There is no cancellation that happens here because log without the base is log base 10. That does not match the base of 1.04. So it's a little annoying that it doesn't cancel, but it comes out okay, right? You get t is log of 2 divided by log of 1.404. Now, obviously, that's your exact answer. That doesn't really mean much unless you're a human calculator. So, I would go to Desmos and type that in, right? So I like to start my fraction. I'm going to do log of 2 over, and then I type it in again, log of 1.04. And it's going to take about 17.67, so almost 18 years for the magic to happen, right? It is what it is, right? So 17.67 roughly. So we would say 17.67 years. Did they tell us where to round to? No, so that's a fine answer. Okay, and like most investments people make in life, they usually are playing out a few different options of what they might want to invest in depending on the things that exist out there for them to put their money in. Now, it's interesting to think about this. So account A is paying 4%, but it's only compounding annually. Account B pays 3.5%, so its interest is lower, but it is compounding monthly, right? So you might think well, it's 0.5% less in interest, so maybe because it's compounded so much more frequently, maybe it's that I'll get more money. Well, let's find out, right? So part D, write an equation for S sub B of t, the amount of money in the account B. I have to fix that at time t. So again, here I got to be a little bit more careful. So the investment amount is the same. It's that 5,000. The rate here is 3.5% or 0.035. And the number of compoundings per year is 12, because if you do something every month, you do it 12 times per year. So now I'm plugging all this stuff in, right? So it's like S sub B of t is P, initial investment of 5,000, times 1 plus 0.035 over N, 12, to the 12 times T. Now, I would just leave it like that, and you're just going to have to carefully type it in Desmos if you want to use it for something. I would leave it like that. So then that leads me to the next natural question is like, which account will have more money after 20 years? Well, we know how much is in account A after 20 years. Let's see how much account B would give me. So S sub B of 20 is 5,000 times 1 plus 0.035 divided by 12 to the 12 times 20. I would not piecemeal this. What do I mean by piecemeal? I would type this whole thing in one shebang on Desmos. If you don't, you're probably going to get some like typo calculator errors. So watch how I do this, and then we'll be done. So it's 5,000, open some parentheses, 1 plus, I would hit the division key now to get that fraction, and you see how my parentheses automatically get bigger. Very nice. So it's 0.035, come down, put the 12 in there, and then close the parentheses, add the exponent, and now, right, it's 12 times 20. I mean, yes, we could figure out what 12 times 20 is, but you can literally type the exponent it is, if I put parentheses anyway, which is annoying, I guess. 12 times 20. You could do that. And you see, while you do have more than $10,000, you know, you actually don't have more than account A gives you. So how much would that be? That would be, so S sub B of 20 would be $10,000, $10,058.51. So, I mean, like, which one is more? It's S sub A. So I would say that since account A at time 20 is more than account B at time 20, account A is the better investment. And I think that is one surprising thing that I purposely did here in this question. Again, account B is getting a smaller interest rate, but you might think because it's compounded so frequently that you might end up with more money, but that's actually not the case. The higher interest rate here gives you more money even though you are only compounding once a year. Anyway, those are a good look at free response style questions for the Unit 4 exam. Hope you're doing well. I will talk to you soon. Bye-bye.